I'd like to discuss planetary atmospheres. As you will see, there is quite a difference in atmospheres of various planets. First of all, there is a great difference between the atmospheres of terrestrial planets on one hand and the Jovian planets on the other hand. And you can kind of understand that because all the Jovian planets are beyond the frost line and they are far away from the sun. The inner part of the solar system was cleaned up from light volatile gases such as hydrogen and helium during the T Tauri phase, when there were powerful solar winds that blew out these light elements. But as you will see, there is also quite a variation in the atmospheres of terrestrial planets, and we would like to understand why. Can we understand why, say, the atmosphere of Venus is so different from our atmosphere? So first of all, what are the sources of planetary atmospheres? Well, on one hand, we have the original gas that was present in the nebula when it started contracting and eventually the solar system was formed. There are, of course, hydrogen and helium. By mass, hydrogen is about 3/4 and helium 1/4. And this original gas is often referred to as a primary atmosphere. In the case of terrestrial planets, there is a secondary source for the gases out of which the atmosphere could form. And these gases were produced during intense volcanic activities on all the planets in the inner part of the solar system, terrestrial planets. So these volcanic gases, they involve carbon dioxide, sulfur dioxide, water, and nitrogen. Okay? These are the important components of volcanic gases. And as I said, only the Jovian planets that are beyond the frost line have primary atmosphere. As you will see, their atmosphere consists mostly of hydrogen in a percentage by mass larger than this one here, and helium, and there are some noble gases, and there is also some methane. Here is the photograph of Jupiter. You can see the high clouds in its atmosphere, and these clouds are composed of the crystals of ammonia in the case of Jupiter. And terrestrial planets have lost the primary atmosphere. So the question is, how can a planet lose the atmosphere? Right? Well, first of all, I said that there was not much hydrogen and helium in the inner part of the solar system because the powerful solar wind just blew it out. But in general, a planet can lose its atmosphere regardless of its composition if it has a very hot surface and if the escape velocity from it is low. So these two things control whether a planet can hold on to a particular gas in its atmosphere. So first of all, what is the role of temperature? Well, in a gas like planetary atmosphere, like the air in this room, the molecules in the atmosphere are moving in a chaotic, random way, like bees in a beehive, right? But they move at different speeds. But the average speed with which they move is determined by the temperature. So the relationship between the temperature of the atmosphere and the average speed of the molecules is given like so. So if the temperature is higher for a given type of molecule, m is its mass, its average speed is going to be higher. So as the temperature rises, the average speed increases. In fact, The temperature just is a reflection of the average speed of motion of the molecules. Moreover, you can see that the smaller the mass of the molecule for given temperature, the average speed of those molecules is going to be higher. Okay? So low mass molecules for a given temperature will move much faster on average compared to the heavier ones. For instance, hydrogen molecule, which consists of 2 hydrogen atoms, will move at much higher speed than, say, the oxygen molecule, which consists of 2 oxygen atoms, and oxygen atom is about 16 times heavier than hydrogen atom, and by the same token, the oxygen molecule is 16 times more massive than the hydrogen, right? So for given temperature of a gas, hydrogen atoms, the light, or rather molecules, the light ones, will move much faster than those that are more massive, say molecules of oxygen. The next component is, I mentioned the escape velocity of any body from a planet or a satellite. And this escape velocity is determined by the mass of the planet and its radius, and the relationship is given like so. The square of the escape velocity from a body is proportional to its mass and inversely proportional to its radius, right? So as the mass grows, the escape velocity becomes higher. As the mass grows, the gravitational pull by the planet increases, and therefore you need to launch a body with higher speed so that it can escape the gravitational confine of the planet. So what could happen if the surface temperature of a planet is very high and its mass is low? We could have that the average speed of a particular kind of molecule is bigger than the escape velocity from the planet, and then those molecules will take off. They will escape into space, right? So in particular, the lighter ones, for which the average speed is higher, they certainly, there is a possibility for them, if the temperature is sufficiently high, for them to have average speed that is bigger than the escape velocity from a planet, and they will just take off. So basically, it turns out when you do the calculation, and I used to, when I was teaching second year mechanics in our physics program, one of the problems was actually for them to find out for particular conditions, particular temperature, which molecules, and for a body of a given mass and radius, say Earth, which molecules will remain in the atmosphere and which ones would just leave. And basically it turns out that for the masses in the solar system, among terrestrial planets, it turns out when you do the calculation and take typical temperatures, that even if they had initially hydrogen and helium, if there was some available in the inner part of the solar system, these light gases would just escape. They would be moving too fast to be kept by a small mass terrestrial planets. So then the question is, okay, so what determines the surface temperature of a planet, right? Because the temperature will dictate which molecules can escape. Right? So there are two factors that determine the surface temperature of a planet. One is the distance from the sun, because the sun is the most important source of light and heat throughout the solar system, right? So the closer the planet is to the sun, it receives more solar heating, right? If you want to warm up on a cold winter day like we had this past winter near the fireplace, you need to get close to it, right? So that you can receive more energy. and the amount of energy that you receive per unit area drops with square of the distance from the source, okay? So the closer the planet to the sun, the more solar heating it receives. That's one factor. The second factor is how much of that heat is reflected back, right? Not all of the energy received from the sun is absorbed, right? Some of the sunlight is reflected. So what determines the fraction of the energy that is reflected back? And the property that describes that is so-called reflectivity or albedo. And by definition, albedo or reflectivity is a percentage of incoming light that is reflected back. So what is the situation? Well, here is a planet with its solid surface here, right? And there are some clouds, if any. Right? And it turns out that clouds have high reflectivity. So they will reflect back most of the energy that they receive. The solid rocky surface has low reflectivity. Most of the energy is absorbed. You know that on a hot summer day, you know, if you are barefoot to walk on your concrete patio or a driveway that has been heated by sun in the morning, you know, it's hot, right? Because lots of energy has been absorbed and the temperature of concrete is relatively high, okay? So, and I've tried to indicate that with these upward arrows that denote the sunlight that is reflected. So less is reflected by the solid rocky surface than by the clouds. Clouds reflect more, okay? So if we have a situation where you have a pure rocky surface with no clouds, then you are dealing with low reflectivity, low albedo, and the surface will absorb most of the received energy. If you have some cloud cover, then you have a medium albedo, a larger fraction of energy is being reflected. And then if it's all clouds, then we are dealing with high albedo, high reflectivity, because clouds reflect the incoming sunlight. So let's look at the values of the albedo of different bodies in solar system, actually planets, but I've also included just our moon because it's our satellite. So Mercury, because practically has no atmosphere to speak of, has very low albedo, right? There is no atmosphere, there are no clouds. So the reflectivity is really low. Venus, on the other hand, has a substantial atmosphere, as you will see, with high and low clouds, and it has very large reflectivity, 72%. Our Earth has reflectivity that is 1/2 that of Venus. Moon, just like Mercury, because there is no atmosphere to speak of, has very low reflectivity, 7%. Mars, 25%, although its atmosphere is relatively thin, but not as thin as in the case of Mercury and Moon. And then the Jovian planets have reflectivities comparable to that of the Earth, right? Around 30-some%. So let's go planet by planet. Mercury at about 0.4 astronomical units away from the sun. It's close to it. It receives a lot of solar heating. It has low reflectivity because, first of all, its atmosphere is very, very thin. The pressure is 10 to the -12 of 1 atmosphere, which is the pressure here roughly on the surface of the Earth. So extremely tenuous atmosphere, and therefore there are no clouds. So it has low reflectivity. Both of these factors cause a high surface temperature on Mercury, in particular the side that is facing the sun. It is a small planet, as we saw earlier when we started discussing the planets, therefore has low gravity, that is the escape velocity from it is low, so basically all the gases have left. There are some in traces. People have found small amounts of various gases that are present there for different reasons, but we can, for all practical purposes, say that it's virtually non-existent. As I mentioned, the atmospheric pressure is less than 10 to the minus 12 atmospheres. Venus, on the other hand, has a substantial atmosphere. The Venus was explored for the first time by Soviets in the 60s, and they sent a probe that was supposed to parachute to the surface of Venus and take the data, temperature, pressure, the basic things, and send it back, okay? Well, they didn't realize how extensive the atmosphere of Venus was, so the parachutes were too big. So the descent velocity was too low, right? It took a long time for it to land, and actually it was so long that the batteries ran out. So the probe didn't reach the surface, okay? The second time, they decreased the size of the parachutes. It managed to reach the surface, but as you will see, the pressure on the surface of Venus is huge. It's about 92 atmospheres, 92 times bigger than the atmosphere on the, than the pressure on the surface of the Earth, right? So they didn't know that, and the probe was crushed. And only in 1970, they managed to land successfully a probe that was able to send the data for about 23 minutes on temperature and pressure, right? And then they had later on 2 more successful probes. That was a program called Venera, which is Venus in Russian. Probes 9 and 7 sent the first images of the surface of the Mars. And then later on, they sent 2 probes, Vega, in mid-80s to explore the Halley's Comet. And as they were passing by, they sent 2 balloons into the atmosphere of Venus, and they were flying at the altitude of about 55 kilometers. And they detected very high winds and very turbulent atmosphere on Venus. So its composition is basically, by and large, it's composed of CO2. 96% of Venusian atmosphere is carbon dioxide. Then there is some nitrogen, and then there are small amounts of sulfur dioxide, water, sulfuric acid. In fact, the clouds on Venus are composed of the droplets of sulfuric acid, and there is very vile, very corrosive acid, hydrochloric acid, present there in the atmosphere as well. So as you can see, the atmosphere of Venus is not really friendly to us. Here is the profile of its atmosphere. On the horizontal axis, you have temperature, and this line here indicates the temperature profile. So for instance, at this particular altitude in kilometers, right, 150 kilometers, I would have to come down, and the temperature is about 200 degrees Kelvin, right? So as we get closer and closer to the surface, the temperature increases, and right at the surface, it's 462 degrees centigrade, okay? I don't cook any dish at that high temperature. And as I mentioned before, because the atmosphere is so thick, the surface pressure is extremely large, 92 atmosphere. And as this diagram illustrates here, the clouds are composed of the droplets of sulfuric acid. So the question is, why is Venus so hot? Why is it so different from the Earth, right? I mean, it's a planet not too much closer to the sun compared to us. It's at 0.72 astronomical units. It's comparable in size, slightly smaller. Therefore, it has similar gravity and escape velocity. So what's the reason for this difference? Well, it turns out that what is responsible for this high temperature on Venus is a runaway greenhouse effect. Now, before I explain what a greenhouse effect is, I want to tell you a few things about how different electromagnetic radiation interacts with gas molecules in the atmosphere. X-rays, they are high energy particles, photons, and they pack a punch. So basically they dissociate the molecules of a gas. They break it up into constituent atoms. They also in the process ionize the atoms. They knock out the electrons, right? So this energy is absorbed. UV radiation, UV photons are also energetic, but not as energetic as X-rays, but they have enough energy to break up, say, water molecule in OH complex and hydrogen. Visible light is transmitted or scattered, depending on the wavelength, by the molecules in the atmosphere. Longer wavelengths, like red, it basically is unaffected, it passes through. And the shorter blue wavelengths is scattered. And we talked about that when we discussed the color of reflection nebula, and we talked in the same context about the color of the sky. That's because the blue light is scattered very effectively, okay? Infrared radiation, on the other hand, it is also absorbed, but it doesn't break up the molecule. It excites it. It starts either rotating, molecule of water, or it starts vibrating. In any event, infrared radiation gets absorbed by certain molecules in the air, in particular water, CO2, and methane. And this is actually behind the greenhouse effect. You see, this is illustration of what is involved. The sunlight, long wavelengths on most of energies at yellow wavelengths. It passes through the atmosphere. Some of that energy is being absorbed by the surface of the Earth, and some of it is being reflected. But basically, what happens, Earth, of course, has to emit energy back, because if the energy is constantly dumped, it would heat up, heat up, heat up. So in equilibrium, as much energy is absorbed by the Earth, the same amount of energy is going to be emitted back. However, not at the same wavelength. The wavelength of radiation depends on the surface temperature, and it turns out that the Earth emits back at a longer wavelength, in infrared, just like we do at our body temperature of about 36, 37 degrees centigrade. We produce electromagnetic radiation at infrared wavelengths. So that infrared radiation that is emitted by warmed up Earth is constantly being absorbed and then re-emitted and absorbed by these so-called greenhouse gases in the atmosphere. And the main culprits are, nobody talks these days about water, but actually water is much more efficient greenhouse gas than CO2, right? I mean, there is a lot of talk about CO2, not without a reason, but I just want to point out that water in the atmosphere is actually more efficient greenhouse gas. So basically the molecules of water, methane, and carbon dioxide, they trap the infrared radiation in the atmosphere and it heats up, okay? And that's why the atmosphere of Venus is so hot. 96% of it is carbon dioxide. It's basically all greenhouse gas, okay? And this we have a runaway greenhouse effect, and as a result, the temperature on the surface of Venus is very high. So you can say, okay, so what makes the Earth so different from Venus? I mean, after all, we are not much further away from the sun by about 30%. Planet has the same size. What's the reason that our atmosphere admits life as we know it, and the one on Venus doesn't? Well, it turns out that the main chief reason is that our distance from the sun is just right, so that the water on Earth exists in liquid form. The temperature on the surface is between 0, the freezing point at atmospheric pressure, and 100 degrees centigrade, the boiling point, again at atmospheric pressure, so that the water exists in the liquid form on Earth. We are surrounded, most of the surface of the Earth is covered by oceans. And it turns out that liquid water absorbs the CO2 from the air. It turns it into carbonic acid. Once the CO2 in the atmosphere is absorbed by liquid water, there is a chemical reaction that produces carbonic acid, and then this carbonic acid reacts with silicate rock, producing limestone. So CO2 effectively gets deposited at the ocean floors in the form of limestone. So as a result, mostly nitrogen was left behind, but also some oxygen was produced as well in the Earth's atmosphere. And the mechanism by which oxygen is produced is the UV radiation, as I pointed out earlier. It will dissociate the water molecule. And if you, say, have two dissociated water molecules, then you will end up, two oxygens will combine into the molecule of oxygen, right? I have two water molecules, two oxygens, they will produce a molecule of oxygen, and then I will have two molecules of hydrogen. Hydrogen will escape because it has low mass, and the Earth's gravity is not high enough to hold it back. It will leave. On the other hand, the oxygen molecule that is 16 times more massive than the hydrogen molecule is left behind. So up to about 2 to 2.5 billion years ago, that was the main source of oxygen in the Earth's atmosphere. That's how the oxygen in the atmosphere was produced. By that time, a certain type of bacteria, cyanobacteria, or blue-green algae, evolved. And these bacteria actually do photosynthesis. They consume CO2 from the atmosphere and water from its surrounding, and through the process of photosynthesis, they produce carbohydrate molecules, for instance, different types of sugar, right? And in the process, oxygen is released as a byproduct. And of course, later on, an abundant plant life evolved, right? And plants do the same thing. Through photosynthesis, they take out carbon dioxide from the atmosphere, and together with water, they produce carbohydrate molecules and release oxygen, right? So after that, the amount of oxygen in the Earth's atmosphere increased rapidly. So the life was necessary for the content of oxygen in the atmosphere to increase. So present composition of the Earth's atmosphere is that it's almost 80% nitrogen, right? And that's good, because nitrogen prevents in a large amount. If it was all oxygen, I mean, the atmosphere would ignite, right? You would turn on, you would light up the match, and the entire atmosphere would go in flames, right? And it's the nitrogen that prevents that. And then, in addition, so 78% is nitrogen, oxygen is 21%, and there are small amounts of water vapor, argon, and CO2. You see, less than 1%. But we have to be careful not to increase the amount of these greenhouse gases in the atmosphere, because atmosphere is a very delicate system. You can all of a sudden trigger certain runaway processes and things could change quickly. So that's the reason why people are concerned about emission of greenhouse gases in the atmosphere. I want to stress that because of their structure, the way they are built, neither nitrogen nor oxygen are greenhouse gases. The Mars has a very thin atmosphere. The pressure is 0.005, 5/1000th of the pressure on the Earth. So it's very thin. The temperature, because there is no atmosphere to moderate the temperature, there are big changes. It ranges from minus 140 degrees centigrade to plus 20 degrees centigrade, right? And then you have here some clouds, carbon dioxide ice clouds, and then some water ice clouds. And composition of Martian atmosphere is similar to that of Venus. So you can say, well, it's 95% CO2. So you can say, well, how come that this large proportion of greenhouse gas did not warm up the temperature of Mars? Well, because the atmosphere is thin. Yes, it's 95% CO2, but total amount of CO2 is small because the atmosphere is thin. So you can say, well, why is this so? Why is the Martian atmosphere so small? It is a small planet, and therefore the escape velocity from it is low, right? So molecules could, in principle, leave. But the key thing is, for its atmosphere being so thin, is that it has no magnetic field. Recall I've talked about it earlier, that a magnetic field shields an object from the charges coming from outer space. Either solar wind, the outflow of charges from the sun, or from cosmic rays that come from deep in space. These are very fast moving protons moving almost near the speed of light. And Mars has no magnetic field, and therefore the solar wind eroded over time its atmosphere. It just pushed it out, right? The solar wind simply depleted the atmosphere of the Mars. And the question is, why doesn't Mars have magnetic field, right? Well, one of the serious hypotheses these days is that basically what happened several billion years ago, that it was struck by a large body. And when it was struck by a large body in the area where the collision occurred, the surface temperature rose, right? Because all of the kinetic energy was transformed into heat. Now, it turns out the actual mechanism is very complicated, but for a body to have a magnetic field, you have to have charges that are being stirred by convection currents. And convection is driven by the difference in temperature. So when the surface heated up, there was no temperature gradient between the interior and the surface. Convection stopped, and the magnetic field was turned off. Okay? And there is some evidence that indeed, not just one, but two large impacts took place a few billion years ago, and it is assumed that that is responsible for the lack of magnetic field on Mars. Now, the Jovian planets are large enough, they have high mass, so that the escape velocity from them is very high. And they're also far away from the sun. They are beyond the frost line. So the amount of solar heating that they receive is low. they could retain, and they did, the primary atmosphere, hydrogen and helium. So here is a photo of 4 Jovian planets: Jupiter, Saturn with its beautiful rings, Uranus, and Neptune. And it turns out that Jupiter's atmosphere is mostly hydrogen. 90% of it is hydrogen. Helium is remaining 10%. There's less percent of noble gas, neon, used in neon lights. There are some amounts of ammonia. In fact, these clouds, as I mentioned before, high clouds on Jupiter, are composed of ammonia crystals. There is some argon and methane. Saturn is very similar to Jupiter in terms of composition of its atmosphere. It's almost 90% hydrogen, about 10%, 11 of helium, neon 1%, and then ammonia and methane. Uranus has a composition similar to that of the Sun. 76% is hydrogen and 23% is helium, roughly 3/4, 1/4, right? Roughly the same as in the original solar nebula. And it turns out that it's the methane that gives it this blue-green color. The color of Uranus is caused by the presence of methane in its atmosphere. And the same story is for Neptune, mostly hydrogen, and the rest is helium. And again, the methane in its atmosphere gives it this bluish color.